Celsius.
Celsius, also known as centigrade, is a scale and unit of measurement for temperature. It is named after the Swedish astronomer Anders Celsius, who developed a similar temperature scale. The degree Celsius can refer to a specific temperature on the Celsius scale as well as a unit to indicate a temperature interval, a difference between two temperatures or an uncertainty. The unit was known until 1948 as centigrade, from the Latin centum translated as 100 and gradus translated as steps. From 1744 until 1954, 0 DEGC was defined as the freezing point of water and 100 DEGC was defined as the boiling point of water, both at a pressure of 1 standard atmosphere, with mercury being the working material. Although these defining correlations are commonly taught in schools today, by international agreement the unit degree Celsius, and the Celsius scale are currently defined by two different temperatures, absolute zero, and the triple point of VSMOW, specially purified water. This definition also precisely relates the Celsius scale to the Kelvin scale, which defines the SI base unit of thermodynamic temperature with symbol K. Absolute zero, the lowest temperature possible at which matter reaches minimum entropy, is defined as being precisely 0 K and 273.15 DEGC. The temperature of the triple point of water is defined as precisely 273.16 K and 0.01 DEGC. This definition fixes the magnitude of both the degree Celsius and the Kelvin as precisely 1 part in 273.16. Approximately 0.00366 of the difference between absolute zero and the triple point of water. Thus, it sets the magnitude of 1 degree Celsius and that of 1 Kelvin as exactly the same. Additionally, it establishes the difference between the two scales' null points as being precisely 273.15 degrees Celsius. 273.15 DEGC equals 0 K and 0 DEGC equals 273.15 K.
History.
In 1742, Swedish astronomer Anders Celsius, 1701 to 1744, created a temperature scale which was the reverse of the scale now known by the name Celsius. 0 represented the boiling point of water, while 100 represented the freezing point of water. In his paper Observations of Two Persistent Degrees on a Thermometer, he recounted his experiments showing that the melting point of ice is essentially unaffected by pressure. He also determined with remarkable precision how the boiling point of water varied as a function of atmospheric pressure. He proposed that the 0 point of his temperature scale, being the boiling point, would be calibrated at the mean barometric pressure at mean sea level. This pressure is known as 1 standard atmosphere. The BIPM's 10th General Conference on Weights and Measures, CGPM, later defined 1 standard atmosphere to equal precisely 1,013,250 dynes per square centimeter, 101.325 kilopascals. In 1743, the Lyonnais physicist Jean-Pierre Christin, permanent secretary of the Académie des Sciences, Belles Lettres et Arts de Lyon Fr., working independently of Celsius, developed a scale where 0 represented the freezing point of water and 100 represented the boiling point of water. On May 19, 1743 he published the design of a mercury thermometer, the thermometer of Lyon built by the craftsman Pierre Cassati, that used this scale. In 1744, coincident with the death of Anders Celsius, the Swedish botanist Carolus Linnaeus, 1707–1778, reversed Celsius's scale. His custom-made Linnaeus thermometer, for use in his greenhouses, was made by Daniel Ekström, Sweden's leading maker of scientific instruments at the time and whose workshop was located in the basement of the Stockholm Observatory. As often happened in this age before modern communications, numerous physicists, scientists, and instrument makers are credited with having independently developed this same scale. Among them were Per Elvius, the secretary of the Royal Swedish Academy of Sciences, which had an instrument workshop, and with whom Linnaeus had been corresponding. Daniel Ekström, the instrument maker. And Martin Stromer, 1707–1770, who had studied astronomy under Anders Celsius. The first known Swedish document reporting temperatures in this modern forward Celsius scale is the paper Hortus Upsaliensis dated December 16, 1745 that Linnaeus wrote to a student of his, Samuel Norkler. In it, Linnaeus recounted the temperatures inside the orangery at the Botanical Garden of Uppsala University.
Centigrade and Celsius.
Since the 19th century, the scientific and thermometry communities worldwide referred to this scale as the centigrade scale. Temperatures on the centigrade scale were often reported simply as degrees or, when greater specificity was desired, as degrees centigrade. The symbol for temperature values on this scale is DEGC. Because the term centigrade was also the Spanish and French language name for a unit of angular measurement, 1/10,000 of a right angle, and had a similar connotation in other languages, the term centesimal degree was used when very precise, unambiguous language was required by international standards bodies such as the BIPM. The 9th CGPM and the CIPM, Comet International des Poids et Mesures, formally adopted degree Celsius, symbol, DEGC, in 1948. It was not until February 1985 that the forecasts issued by the BBC switched from centigrade to Celsius. For scientific use, Celsius is the term usually used, with centigrade otherwise continuing to be in common but decreasing use, especially in informal contexts in English-speaking countries. The French grade is known as the gradient, grad, or gon in English.
Common temperatures.
Some key temperatures relating the Celsius scale to other temperature scales are shown in the table below.
Name and symbol typesetting.
The degree Celsius has been the only SI unit whose full unit name contains an uppercase letter since the SI base unit for temperature, the Kelvin, became the proper name in 1967, replacing the term degree Kelvin. The plural form is degrees Celsius. The general rule of the International Bureau of Weights and Measures, BIPM, is that the numerical value always precedes the unit, and a space is always used to separate the unit from the number, for example 30.2 DEGC, not 30.2 DEGC, or 30.2 DEGC. Thus the value of the quantity is the product of the number and the unit, the space being regarded as a multiplication sign, just as a space between units implies multiplication. The only exceptions to this rule are for the unit symbols for degree, minute, and second for plane angle, deg, and, respectively, for which no space is left between the numerical value and the unit symbol. Other languages, and various publishing houses, may follow different typographical rules.
Unicode character.
Unicode provides a compatibility character for the degree Celsius at U+2103, decimal 8451, for compatibility with CJK encodings that provide such a character. As such, in most fonts the width is the same as for full-width characters. Its appearance is similar to the one synthesized by individually typing its two components, deg, and c. Shown below is the degree Celsius character followed immediately by the two-component version. When viewed on computers that properly support Unicode, the above line may be similar to the image in the line below, enlarged for clarity. The canonical decomposition is simply an ordinary degree sign and c, so some browsers may simply display DEGC in its place due to Unicode normalization.
Temperatures and intervals.
The degree Celsius is a special name for the Kelvin for use in expressing Celsius temperatures. The degree Celsius is also subject to the same rules as the Kelvin with regard to the use of its unit name and symbol. Thus, besides expressing specific temperatures along its scale, for example, gallium melts at 29.7646 DEGC, and the temperature outside is 23 degrees Celsius, the degree Celsius is also suitable for expressing temperature intervals, differences between temperatures or their uncertainties, for example. The output of the heat exchanger is hotter by 40 degrees Celsius, and our standard uncertainty is ±3 DEGC. Because of this dual usage, one must not rely upon the unit name or its symbol to denote that a quantity is a temperature interval. it must be unambiguous through context or explicit statement that the quantity is an interval. This is sometimes solved by using the symbol degc, pronounced degrees Celsius for a temperature, and deg, pronounced Celsius degrees for a temperature interval, although this usage is non-standard. What is often confusing about the Celsius measurement is that it follows an interval system but not a ratio system. That it follows a relative scale, not an absolute scale. This is put simply by illustrating that while 10 degc and 20 degc have the same interval difference as 20 degc and 30 degc, the temperature 20 degc is not twice the air heat energy as 10 degc. As this example shows, degrees Celsius is a useful interval measurement but does not possess the characteristics of ratio measures like weight or distance.
Coexistence of Kelvin and Celsius scales.
In science and in engineering, the Celsius scale and the Kelvin scale are often used in combination in close contexts. For example, a measured value was 0.01023 degc with an uncertainty of 70 UK. This practice is permissible because the magnitude of the degree Celsius is equal to that of the Kelvin. Notwithstanding the official endorsement provided by Decision No. 3 of Resolution 3 of the 13th CGPM, which stated a temperature interval may also be expressed in degrees Celsius, the practice of simultaneously using both degc and K remains widespread throughout the scientific world, as the use of SI-prefixed forms of the degree Celsius, such as UDC, or microdegrees Celsius to express a temperature interval has not been well adopted.
Melting and boiling points of water.
One effect of defining the Celsius scale at the triple point of Vienna standard mean ocean water, VSMOW, 273.16 K and 0.01 degc, and at absolute 0, 0 K and 273.15 degc, is that neither the melting nor boiling point of water under one standard atmosphere, 101.325 kilopascals, remains a defining point for the Celsius scale. In 1948, when the Ninth General Conference on Weights and Measures, CGPM, in Resolution 3 first considered using the triple point of water as a defining point, the triple point was so close to being 0.01 degc greater than water's known melting point, it was simply defined as precisely 0.01 degc. However, current measurements show that the difference between the triple and melting points of VSMOW is actually very slightly, less than 0.001 degc, greater than 0.01 degc. Thus, the actual melting point of ice is very slightly, less than a thousandth of a degree, below 0 degc. Also, defining water's triple point at 273.16 K precisely defined the magnitude of each 1 degc increment in terms of the absolute thermodynamic temperature scale, referencing absolute zero. Now decoupled from the actual boiling point of water, the value 100 degc is hotter than 0 degc, in absolute terms, by a factor of precisely, approximately 36.61% thermodynamically hotter. When adhering strictly to the two-point definition for calibration, the boiling point of VSMOW under one standard atmosphere of pressure is actually 373.1339 K, 99.9839 degc. When calibrated to ITS 90, a calibration standard comprising many definition points and commonly used for high-precision instrumentation, the boiling point of VSMOW is slightly less, about 99.974 degc. This boiling point difference of 16.1 millikelvin between the Celsius scale's original definition and the current one, based on absolute zero in the triple point, has little practical meaning in common daily applications because water's boiling point is very sensitive to variations in barometric pressure. For example, an altitude change of only 28 centimeters, 11 in, causes the boiling point to change by 1 millikelvin.
Worldwide adoption.
Throughout the world, except in the United States, Belize, Parlay and the United States territories of American Samoa and the U.S. Virgin Islands, except Puerto Rico and Guam, with the former predominantly using Celsius and the latter equally using Celsius and Fahrenheit. The Celsius temperature scale is used for practically all purposes. The only exceptions are some specialist fields, for example low-temperature physics, astrophysics, light temperature and photography, where the closely related Kelvin scale dominates instead. Most scientific fields and many engineering fields use the Celsius scale, and the metric system in general. However, most Americans remain more accustomed to the Fahrenheit scale, which is the scale that U.S. broadcasters and journalists use in weather forecasting, although the equivalent in Celsius is occasionally provided alongside. Fahrenheit is also commonly used in the U.S. for measurement of body temperature, and household use such as cooking, and is the scale commonly seen on ovens and in recipes. In Canada, kitchen devices, literature, and packaging include both Fahrenheit and Celsius quotations. The United Kingdom has gradually increased use of the Celsius scale since the 1970s and it is now the predominant temperature scale used. Some broadcasters and publications quote Fahrenheit air temperatures alongside Celsius in weather forecasts while others use Celsius only. Likewise, some retailers sell air temperature thermometers that show both scales, but most now display Celsius only, and Fahrenheit only displays are extremely uncommon.
Conversion table between the different temperature units.